Good day. We are going to look at how to predict redox reactions. We're going to go through the steps very briefly once again. So you had this in the previous notes, is exact same the first two slides. You list all the chemicals, correct formulas, classified as an oxidizing agent, reducing agent, or both. Figure out what the strongest oxidizing agent is. Figure out the strongest reducing agent. Write down their half reactions. Come up with a redox equation. Come up with a voltage, or from the position, figure out if they're spontaneous or non-spontaneous. So we're going to look at these examples, and we'll do 2 examples per video. So we'll look at 31A, zinc plus hydrochloric acid. So you're going to have to copy these down. OA on the left means oxidizing agent, RA on the right means reducing agent. Well, when I look at zinc, I have to understand that's zinc metal. That's not Zn2+, not a compound. So it's just zinc, Zn. It's going to be a reducing agent. Hydrochloric acid, that means I have HCl, but I have to recognize it's going to split into H plus and Cl minus. And I have to classify those things. And because it's a water-based solution, we have to worry about water. So there's our zinc. There's our H plus from the acid. There's our chloride from the chloric part of the acid, and then we should put in our waters. And water you'll find in the chart on both sides, and water tends to be a fairly weak oxidizing agent, fairly weak reducing agent. So often we don't even run into it reacting. When I come down on the periodic table, I look and I go, oh, I hit the H plus before I hit the H2O. So I would circle that, you can circle that. When I go up on the right, I'm going to see I hit the zinc, and then I'd actually, strangely enough, hit the chloride, then I hit the water. But I'm going to circle the zinc because it's the strongest reducing agent out of these beasties. So I've made them orange or red here. You should circle both of those. Once you've done that, you've done the hardest part of the question. Now we go to the chart, and we see, hey, there's the reduction of hydrogen, and now we need the oxidation of zinc. And there's our overall reaction. And hydrogen is above zinc, diagonally positioned like so. And so it is spontaneous. That's a reaction that's going to happen naturally. So we know that. You've put zinc and hydrochloric acid in previous courses, and it's fizzed madly. And that's because hydrogen's a better oxidizing agent than Zn2+. We'll do another example. Here's chlorine gas. Got to remember it's diatomic, Cl2. We have iodide ions. They're I minus. And we're going to have water. So we don't have too many choices here. So OA and RA. There's our chlorine. There's our iodide. Every time we have water, we put it on both sides. We're going to come down the left, and we're going to find that we hit chlorine first. And when we go up on the right, we're going to find iodide first. So you circle that, and you circle that. Now we know we need a half reaction involving reduction of chlorine and a half reaction involving the oxidation of iodide. When we look at how they're positioned, well, first of all, we get this overall reaction. And we have an arrow like so. And it turns out that arrow is correct. An arrow pointing the right does mean spontaneous. Chlorine is above iodine, and so therefore it's positioned diagonally like so, and the reaction will happen. That's a good place to stop for this one, and we'll carry on with our next example in the next video.